Well, good afternoon, everybody. So this is the last lecture of new material for the semester, and we will just be finishing off the chapter on water today with a few extra topics woven in. And so where we left off last lecture, I guess it was before the exam, was talking about solubility of different compounds. And so these are, this was a table that, again, you should be familiar with some of these rules that, for instance, all nitrates are soluble, all group 1 metals are soluble, and so some of the exceptions that aren't soluble. And so this would be something, to have on your cheat sheet for the final exam if you don't want to memorize these rules. And so today we're going to talk about a couple other concepts, and so that is an electrolyte and a non-electrolyte. These are terms that you may see in products. For instance, Gatorade, says it replenishes electrolytes, but not everybody really knows what does that mean. And so electrolytes are just really something that completely dissolves in solution. Okay, and so we'll just say dissolves in solution. And if it is a strong electrolyte, that is, for an instance shown here on the slide, like sodium chloride, if it's a strong electrolyte, that just means that it is 100% dissociated. So that means AQ. So if you have a solid that is dissolving in water, the AQ just means that you now have an aqueous solution. Okay, or this solid has been dissolved 100% in water. Okay, so that's a strong electrolyte. And then weak electrolytes would be some of these salts that are just, maybe mostly insoluble, for instance. So let's say calcium carbonate, for instance. It's insoluble in water, so that would be a weak electrolyte. Okay? And if something is not broken apart at all, like sugar, so that's C6H12O6, for instance, and you put that in water, so this is a type of sugar, it's not going to break apart. It'll actually stay, 12O6. So it goes from solid and now aqueous. Okay, so it's dissolved. Whoops, I totally messed this up, but I think you get the gist. Okay, so it keeps its same formula, but it goes from solid to aqueous. Okay, so it doesn't break apart into like carbons, hydrogens, and oxygens separate. Okay, like ions, like this example. Okay, and so this would be a non-electrolyte. Okay, so again, strong versus weak means how much of it goes into solution. Like how much does it break apart, I guess is the best way to talk about it. So a strong electrolyte, 100% dissociated. A weak electrolyte is much less usually than 100% dissociated. Sometimes only like 2% or something like that. And then a non-electrolyte is 0% dissociated. Okay, it still could be soluble in water, like sugar dissolves in water, but it doesn't break apart, so it's 0% dissociated. Okay, and so you can determine this. It's a cool little demo. If you put some electrodes into water, so this is a positive electrode, a negative electrode, and you run those to wires that go through a light bulb. And so you pass a current through this solution. If you have a non-electrolyte like sugar, or just water, just distilled water, for instance, you won't get any light. So this is not lit. I don't know if you can see that too well. But if you put salt water, like sodium chloride, if you put some of that in the water, now you have an electrolyte solution. So when the current comes in, you actually are able to pass current through this electrolyte solution, and it will light the bulb. Okay? So when ions are in aqueous solutions, those solutions are able to conduct electricity, as shown by this difference. Non-electrolyte, no current. Electrolyte, you have current. Okay. So this kind of just summarizes what I blah-blahed about here on the whiteboard here. So if it completely dissociates into ions, it's a strong electrolyte. And then if it only partially dissociates, that's a weak electrolyte. And if it dissolves in water, but it doesn't break apart into ions, then it's a non-electrolyte. And so this is sucrose, a different sugar here, disaccharide, because you've got two kind of units. Okay, and so this does not dissociate. Okay. All right, so we're going to talk about some applications here, some pretty common, relevant applications to our world these days, and it's all going to exploit like dissolves like. And so we spent a lot of time this semester, probably more than what you wanted to spend, talking about bonding in molecules, and then once we know the bonding, we can determine its shape. And then how do individual molecules come together? And those were intermolecular forces. And then from all of that, we could determine, whether these molecules then were polar or nonpolar, depending on the IMFs that they had. And so this like dissolves like, the like here refers to polarity. Okay, and so I think I already mentioned this. So a polar compound like ethanol, and so this is ethanol. Okay, it's polar because if you were to do the Lewis structure of this, I won't show the hydrogens just as lines here. Whoops, it's actually bent, right? Okay, and so I think you would agree that these bond dipoles, they wouldn't cancel. Right, so you've got a carbon oxygen here, and then a hydrogen oxygen, and so there's no way that these dipoles would cancel. So this is a polar molecule, and so if another one of those comes around, okay, now you would have the possibility for hydrogen bonding. Okay. So between oxygen on this one and a hydrogen on this one, okay, because you've got an oxygen directly connected to a hydrogen. Okay, so this is H bonding there. All right, so if you have a polar molecule like ethanol, it's going to want to dissolve or be miscible with another polar substance like water. Okay, so that's why ethanol and water mix very well. But if you have a nonpolar compound like oils or organics, for instance, this is methane, okay, that will not dissolve in water because this is nonpolar and water is polar. Okay, and so this is an example of oil, like just let's say vegetable oil or some kind of other cooking oil that you're pouring in water. And you notice, I think you know this from the kitchen, that these two do not mix completely, right? And so that's because you've got unlike liquids, right? The oil is nonpolar and water is polar, okay? All right, so acid base is where we're going to end today. Let me just show you some other examples for like dissolves like. Okay, and so the first example I'm going to show you is dealing with how do soaps and detergents work. And so if you look in the ingredient list of your shampoos, soaps, that kind of thing, this is a common ingredient, and so it's a mouthful, pentaerythryl palmitate. And so it's got a very long carbon chain. So this is 14 carbons and then another one and then one here. So a long chain. This is what we call a space filling model for it, where the gray here is carbon, whites are hydrogens. And so you've got this long non-polar chain. And then on this end, notice that you've got a bunch of OH groups. And so this, I think you would agree that this is quite polar. Okay, so you've got one end of the molecule that's polar, the other is non-polar. And so what happens is that your dirt particle, which is generally it's organic, so it's going to be oily in nature, that is going to be bound to this non-polar part, again, like dissolves like, and then this polar part's going to be attracted to water because water is polar. And so basically this wraps around the dirt in your clothing, let's say, in a detergent or in a washing machine. So this end wraps around your dirt particles that are on your clothing fabrics. And then this end sort of pulls that oil from your fabric into the water. Okay, so the polar end is attracted to the water part. Okay, so that's how surfactants work, or soaps, detergents. Another application for that is these days talking about coronavirus. Okay, whoops, oh, this chair is very squeaky. And so with coronavirus, this is just a schematic. It's much more complex than this, but this is kind of what it's composed of. And so you've got kind of on the outside of coronavirus, you've got lipid membrane and other proteins. And so these are very non-polar. And so what happens is, again, this is a schematic of soap particles. This is why you should be washing your hands very frequently. And so this is this ball represents the polar end, and then this is that long non-polar chain. And so what happens is, when you're washing your hands, you put soap on your hands, and you've got water, and you're mixing it around. The non-polar part is attracted to the non-polar membrane of the coronavirus, and it literally breaks it apart. So these ends, again, are connected or associated to water. And so as it's driving this toward water, it's ripping it apart because these are already kind of wrapping around this cell membrane. And so it pries apart this coronavirus, and you basically get these different fragments that are surrounded by what we call micelles, or just the wrapping around of these soap particles around each of these fragments. So that's a micelle. Okay, and so this is very soluble in water, and so this then will be rinsed off your hands and down the sink. Okay, so that's why you should really, they say to, I don't know, sing happy birthday or, a song a couple times or something. You should be washing your hands, for quite a long time. And, then you've got sort of frictional forces that kind of help this process to really, make sure that these soap particles can really interact with the cell wall and break it apart. Okay. There was a video that I did in the spring, when all this was really hitting the fan. And this video I put together as kind of a demo, and it really took off. So I had 9 and 10 News visit me at home and do a story, and so I don't know why. It was just kind of a simple video. But this is something you could do, in your classrooms, as you start your teaching careers. I'm sure, I'm hoping coronavirus will be long gone by then, but who knows? We could have another replacement something. And so This is just kind of showing the difference between soap versus hand sanitizer, and why washing your hands with soap is actually more effective than hand sanitizer. And so I'll just maybe play this. It's just a short little, less than a minute video. Okay, so pretty simple. Right, how do I cancel? There we go. Okay, so yes, there's a little demo just kind of showing that after a while the hand sanitizer just sort of fizzed out. And so, as the main ingredient really in hand sanitizers is alcohols, so it could be ethanol, methanol. And so they are fairly volatile, which means they'll evaporate after a while. And so once they evaporate, that's it. It's not really functioning anymore. And so, they are effective, but as long as you have alcohol on your hands. And so you have to really keep applying pretty frequently with sanitizer. And with soap, it's kind of a more brute force method, as we talked about, where it's kind of ripping apart the coronavirus. The alcohol is really not as effective at ripping apart coronavirus. It can destroy the cell wall similarly as soaps, but it's not as effective. And so kind of the take home is there's no substitute for washing with soap. That's really the best way to get rid of any kind of viruses on your hands. All right, and then I wanted to just show you one last application for like dissolves like, or really talking here about like binding like. And so these are a variety of really dangerous illicit drugs. Some of these, I guess, are illicit, like heroin. Some we can get in hospitals, if you're undergoing surgeries. And so what you'll notice, these are sort of the gamut from morphine, codeine, which you can get in cough syrup kind of formulations. You'll notice even oxycodone, which was the drug that he had a whole bunch of drugs in his system, but Michael Jackson, he died overdosing on oxycodone, sometimes called Oxycontin as the trade name. And what you'll notice is they have very similar structures, all of these. So this is the backbone for all of these. So morphine, codeine, heroin have this backbone, and all you're doing is just changing the R1, R2, or R3 groups into different things. And so if you have morphine, for instance, this is going to be an OH group, and this is going to be an OH group, okay? Versus, codeine, this is going to be an O with a CH3, so it's not going to be able to hydrogen bond from this end, whereas this will be an OH, so this can hydrogen bond. So, morphine, when you have these drug receptor sites in your brain, morphine is much more effective for pain relief, but much more addictive also, because you've got two parts that can hydrogen bond versus, codeine is not as effective, and so you only have one end. And then some of these, you have a little different structure, so you'll notice the 6, you've got an O with a different group here. You've got a double bond with O, and then a different substituent here. So it's very similar But again, just a couple groups are different. And so that, hydrocodone, oxycodone, all those differences are just different functional groups on those sites. And so if you look at, the very complicated binding site in your brain, so the receptor site, it's a whole kind of a mess of different kinds of amino acids. So it's this really complex, I don't know if they have I guess this paper they don't have a far away kind of image, but you can kind of see in the background, all of these protein structures. You've kind of got this folded structure that doesn't look that different from DNA, kind of like a helical structure. And then you've got this binding site, this mu opioid receptor site, which is shown here. And you've got a couple important modes that your drug can bind in this site with. And so this blue background means that it is fairly non-polar. And so, in this drug, this part of the drug is quite non-polar. Okay, so you don't have any like OH, NH groups or anything like that. And so this can kind of sit in this little cavity. And then you've got hydrogen bonding, this OH and another OH here. So that would be, so red is the oxygen here. And this is tyrosine, so one amino acid that's in this protein. So tyrosine, that amino acid, is hydrogen bonding to those two OH groups on, in this case, this is morphine. Okay? And so then, you can have drugs that will help people. So there's one called naltrexone, and this is something that is not really carried with police or first responders to like a drug overdose. It's not that fast acting, but it is something that people are treated. If they are addicted to these opioids, they will give them treatments with naltrexone. And so this is called an antagonist. And what that does is it will bind to the receptor site. So you'll see it, binds quite similarly to the actual drug morphine. And it's got a similar structure, again, just some different groups here. And that serves a couple purposes. It, just a second, sorry. So if this is the schematic of just the receptor site, this is what happens, if morphine, for instance, binds that receptor site. It fits in this site a certain way, and then it causes some cellular response. Okay, so it sends a signal to inside of the cell that, says, hey, I'm happy, and, I don't have pain anymore, kind of thing. And that's what makes it effective, but very addictive. And so when you have an antagonist, it has a similar structure, and it'll bind similarly, so it fits again. It's kind of like this lock and key model, so it fits in that site, but you don't get any cellular response. And so it actually blocks it, so the real drug can't get in. Okay. And so so that's how this antagonist, naltrexone, actually binds in there. So again, it's binding to, it looks like a couple different, so it's got tyrosine, that one amino acid, but it's also binding to another lysine amino acid. So it's a similar binding effect, but different enough that it won't cause an overdose with the opioid. And so there's a couple different drugs that are given. So naltrexone is this one that I just showed. The one on the left is naloxone. So this is sometimes called Narcan, and this is the one that if somebody is ODing, like on the street or whatever, first responders or police, they actually will carry a syringe of this with them, of Narcan. And, if they inject this into the person who's ODing, they will get an instant effect. So this is such a strong binding drug that it will instantly kick out the drug. Okay, so if this is already bound in the receptor site, this one is so effectively bound, and I guess it has to do with, again, you've got OH groups that can hydrogen bond so effectively that it will kick this off and replace it with that non-harmful drug. Okay, and so people, can be revived. I think, it all depends how long the person has been, how long since they have, ingested that drug. But there's kind of a time window where that drug can kick this one off, and then the person can, not die from that overdose. All right, so again, this is kind of the long-acting version, and this is the fast-acting one. And you look at these and say, well, the only group that's different, this is what we call a cyclopropane. So it's a 3-carbon ring here. Okay, and then this one is ethylene, so it's just a double bonded carbon-carbon. And so it must have to do with the way that these groups, when they're interacting with those amino acids, that this may influence how the drug can, approach and effectively bind. It is effective, but it's not like instantaneous like this one. And so it's just, sometimes it's really hard to explain why. We just know that this one acts more slowly than this one. Okay, but they're both very effective against opioid addiction. Okay, so so something we're dealing with a whole lot in the U.S. and other countries, opioid addictions, and so your knowledge on intermolecular forces and hydrogen bonding especially, but London dispersion, also is involved here. The nonpolar interactions, all of that is really important in governing how do these opioids work, and then how can we prevent opioid addictions. All right. So let's talk about the last topic here, and that is acids and bases. And so something you hopefully have seen before, maybe in a class a few years ago or so, but really, is kind of property-wise, acids generally have a sour taste. I wouldn't recommend you tasting them to determine if it's an acid or base, though. So this is really kind of an antiquated definition of an acid. You'll see this in a lot of textbooks, that acids have a sour taste, but I would not want to taste hydrochloric acid. I think that would probably eat your tongue off. So that's just a definition, I guess. And then they change the color of an indicator. There are these pH strips that you'll typically have, for instance, if you have a swimming pool is one common example, and they're usually, a certain color, like they could be blue or red, and then when you dip it in an acidic solution, they will turn a different color. Okay, and it's usually, if it's blue, that means that it's basic, and that means a pH greater than 7, and if it's red, it is acidic, and that's a pH less than 7. Okay, and so really the definition of acids, there are a few different definitions. One important definition is the Bronsted definition, and that is that an acid is a H+, which is known as a proton donor, and a base is an H+ acceptor. Okay, and so if you have this reaction, Okay, we would say that this is the acid, okay, because it is donating a proton to the base, which accepts the H+. Okay, so now this has picked up that proton, and then this is now left over because you've lost that proton. Okay. All right. And so, not unlike what we talked about with electrolytes, if it's a strong acid, it is 100% dissociated. So HCl would be a strong acid. And some other strong acids, so you've got HCl, you've got HI, HBr, HNO3, which is nitric acid. Okay, this is hydrobromic acid. This is hydroiodic acid. And then I'm sure you've heard of that one. So this is sulfuric acid. And another one is HClO4, which is perchloric acid. Okay, so those 1, 2, 3, 4, 5, 6 are really the our most common types of strong acids. So those will 100% be broken apart into H+ and then whatever's left. Okay, there are other weak acids which are less than 100% dissociated. And for instance, HF, okay, hydrofluoric acid is one. And it's kind of interesting because if you look at the group 17s, all the other ones like HCl, Br, and I, they're strong, but HF is weak. And it has to do with the bond strength. So, if you were to look at electronegativity, you would think that, this is the most electronegative element in the periodic table. So that should be very strongly moving electrons toward the F-. And so that should, then you would think, it should break apart more easily then. But actually electronegativity is not really the rationale. It's, this is true. This is true that, it would want to dissociate. But this bond strength is so strong that you just can't break that as easily. Okay, and in general, as you go down a group, the bond strengths get weaker. We'll just say X, where X is each of these ones. So the bond strength is weaker. So therefore, HI would be the strongest acid, followed by HBr, HCl, and then that's the weakest. Okay, so all right. Okay, and it has to do, it's kind of involved like why, bonding generally gets weaker as you go down a group at the periodic table, just because the orbitals involved in bonding are smaller. So with fluorine, hydrogen is a small orbital, fluorine is also small, and HCl may look like that, and then an HI may look like this, where iodine is really big, so you only get overlap in a real small area of the iodine, versus with H and F you can approach very closely because they're both really small. Okay, so I know that's TMI, but anyway, so weak acids, HF is one. This is another common one. So this is acetic acid, or in the kitchen we know this as vinegar. Okay, so also a weak acid, which means, where HCl or any strong acid, we write it like this. Okay, just an arrow. for any of these weak acids, we would write it as this. Okay, where this is an equilibrium, where it means that, you just have some in this direction and some in that direction, which means it's really not being dissociated. And with these weak acids, it's actually probably better to write the equilibrium like this. Okay, where it's just a little bit going forward, like it's maybe 5% dissociating. Most of it is undissociated. Okay, so that's why the back arrow is bigger than the forward arrow. Okay? All right. All right, so if you have an H plus ion, so notice all these acids, whether they're strong or weak, this is kind of what we have in solution, but that doesn't exist just by itself. So as soon as you have H plus, you have waters around with it. And so that's why we typically will call a solvated proton H3O plus. Okay, so it's just water with another proton. Okay, and this is a special name for this ion. So the hydronium ion is H3O plus. Okay, but you really could talk about H plus is really the same thing as H3O plus. Okay, so you could use any reaction just with H plus. Okay, so we use them really synonymously. Okay, so with HCl, for instance, you can talk about it doing this. Okay, where you just have that. Or you could talk about HCl in water, where you've got H3O plus Cl minus. Okay, so both of these are really the same thing. We're just talking about an acidic species in solution. Okay. All right, and then bases, they're generally, it's not recommended again to taste, but they're, instead of being sour, they're kind of bitter, I guess. I don't know. I've never tried. It's a slippery feel, so if you get some dilute, hopefully, base on your hands, they'll feel slippery to your skin. And as I mentioned, if you get a litmus paper, it's generally blue if it's a basic solution. And in this case, the strong bases are any of the group 1 or 2, except beryllium, hydroxides. Okay, so group 1, that would be like lithium hydroxide, for instance, or group 2, that would be like barium hydroxide, okay, or magnesium hydroxide, etc. Okay, so all of these are strong bases, which means that they would 100% dissociate into that and an OH minus. Okay. All right, so group 1 or 2 hydroxides, like potassium hydroxide is another example here. And then what's noteworthy is, as I show over here, the group 2, remember, the group 2s will have a 2 plus charge, and hydroxide is just a -1. So you need 2 to balance out the overall charge. We get a -2 and a +2. Okay, and so if it's a group 2 hydroxide, then you're generating 2 hydroxides for every mole of this. Okay? And so those are the strong bases. Weak bases are very typically where you've got nitrogen with 3 substances or groups connected to it. So they could all be hydrogens. So this is called ammonia. Okay? And so all of these are weak bases. All right, and so ammonia is one, or you could have a combination where maybe you've got one hydrogen and then different groups here. So you could have let's say this. Okay, so that's another type of weak base. Okay, or where you have 3 different groups, like this one. Okay, they could either be the same or they could be different. Okay, so these kind of just could be whatever you want, these different groups. But it's connected to a nitrogen most commonly. Okay, so those are all very common types of weak bases. Okay, and shown here, the equilibrium, if you add the base to water, now this is a base, so it's going to accept a proton. And so water in this case, instead of it taking on a proton, it's actually going to donate this. And so now you've got an OH minus, okay, and now you get an NH4 plus, okay, because this has accepted the proton. Okay, so notice that water in the previous example, so we had this, right? That, right? So water is acting as a base, right, because it is accepting a proton, okay? Or, in this example, okay, now it's acting as an acid, right, because it is donating the proton to the base. Okay, so water can serve as both a base and an acid, and so that is known as an amphoteric substance. Okay. All right, I'm not going to focus really a whole lot on neutralization reactions. In past semesters we've gone, for ionic equations, and I kind of went hardcore on this. I'm really not going to go any more than this one slide. And so we've talked about other types of reactions in this class. Most noteworthy, I guess, is combustion reaction, where you have a fuel plus oxygen goes to CO2 and water. Okay, so this is a combustion. This is a neutralization reaction, where you've got an acid and a base together, and what you get is a salt and water. Okay, so you're going to get some kind of a ionic compound as one of your products, and water. Okay, so I guess one type of question on the final would be, giving different types of reactions, and which one is a neutralization reaction. You're just looking for something where you've got an acid and a base, and you're going to get a salt and water. Okay. All right, so pH is a way to mathematically determine, how acidic, how basic something is, a solution is. And this is the important equation. Okay, so pH, to calculate the pH, you take the negative log of the proton concentration. And so let's say the proton concentration is 1 times 10 to the minus 3. You should have a button on your calculator, log, or maybe it's log x or something like that. And so you would just literally type in log of 1 times 10 to the minus 3, okay? And you will get an answer on your calculator of minus 3, okay? But pH is minus log of the proton concentration, okay? So we take the opposite of the sign, so that's why the pH then is a positive value, okay? So I guess maybe shown here more directly. So pH is minus log of it, so it's a minus of the minus 3, so that gives you a positive 3, okay? And so what is noteworthy here is that this is a log scale, and so a pH of 1 is actually 10 times more acidic than a pH 2, okay? And then this is 10 times more than pH 3, okay? So every 1 unit represents a power of 10. Okay, so factor of 10. All right. Oops. All right, so we can, I think this is probably a little too complex, really. I'm not going to get into this really this semester. Well, I guess what's important for this semester, I think, is just really knowing what pH values you have for acidic, basic, or a neutral solution. And so in a solution where all of the proton concentration is equal to the hydroxide, so this corresponds to base, I guess basicity, this is acidity. So if those concentrations are equal, you have a neutral solution, and that'll be a pH of 7. If the protons are greater in concentration, that means you have an acidic solution, so your pH will be less than 7. And then if your hydroxide is greater in concentration, that is a basic solution, so the pH will be greater than 7. Okay? All right, so this is some common type of household items and other things, I guess, like blood here, and what their kind of nominal pHs are. And so oven cleaner, very basic, so it's really kind of caustic to your hands. Make sure you always wear gloves if you're dealing with household cleaners. And so household ammonia is quite basic. So this is neutral again, so pure water is 7. And then anything here greater than 7, this is basic. Okay, so we'll have higher hydroxide concentrations. And then anything here will be acidic. And so like tomato juice, Coca-Cola, lemon juice, stomach acid is quite acidic, like 1 point something. Okay, so acid rain is typically like between 3 to 5. Okay, and notice that normal rain, so if you collect rainwater, you'll actually notice that the pH will be normally about like 6 or something, between 5 and 6. And we'll talk about that here in just a few slides. Okay. All right, so just a few comparisons here. So if we have this as one equation, okay, what's really easy is if you have a number like 1 times 10 to the minus 3, and then all of these, it's a concentration, so it's going to be in moles per liter. If you take the negative log of this, you'll get 3. Okay, so it's kind of just whatever this exponent is, so it works out really nice as long as you have 1 times 10 to that. Okay, but if I give you a different value, it's not that simple, and you have to actually use a calculator. So if we have a concentration, let's say 2.3 times 10 to the minus 4. Okay, what is the pH? Okay, and so if you plug that in your calculator, let me do it on mine here. So 2.3 e to the 4 minus, and then you do log of that. Where is that on mine? Okay, so I get, if you take just the log of this, your calculator should say minus 3.64. Okay, and so again, it's minus log, and so your pH then will be 3.64. Okay, and with significant figures, it's worthwhile pointing out, logs are a little different rules for sig figs. So whatever your sig figs are in the concentration, so here this is 2 sig figs, then your pH, after you do the log, in this case negative log, it should have 2 decimal places. Okay, so again, your concentration, what you're doing the log 2, you're doing just sig figs, and then your pH afterwards should have that number but as decimal places. So this has 3 sig figs total, but 2 decimal places to match the 2 sig figs that you had in that number. Okay. All right, and then the other flip side is, let's say I give you a pH of 5.21. What is the H plus concentration? Okay, so to do that, you should have a button on your calculator, this. Okay, and so what you're going to do, again, its pH is negative log of H plus concentration. So the way to go from pH to H plus is you go 10 to the minus pH. Okay, so in this case you would plug it in your calculator as 10 to the minus 5.21. Okay, so let me try that. So do 5.21 minus, or negative, and then 10 to the x. So that is 6.2 times 10 to the minus 6 moles per liter. Okay, and again, your pH has 2 sig figs, or sorry, has 2 decimal places, so you should have 2 sig figs in your answer. Okay, so always look with pH, it's all about the decimal places. Concentration, it's all about sig figs. Okay. All right, so for any of these then, so you know which is more acidic. Okay, so pH of 4 versus 5, so the smaller the number, the more acidic it is. Okay, so tap water is going to be more acidic in this case than ocean water. Tomato juice is more acidic than milk. Okay, and then to do hydrogen ion concentrations, if we do this last one here, so a pH of 4.5, okay, you would do 10 to the minus 4.5. And that is, I guess here you only have 1 decimal place, so that's really just 3 times 10 to the minus 5. So 1 sig fig here. Okay, and then we're comparing that to the 6.5 pH. Okay, so that's 6.5 negative. And so that's 3 times 10 to the minus 7 in this case. Okay, so notice that this has a higher proton concentration by 2 orders of magnitude. Okay, so this is higher, and so therefore it is more acidic. Okay, and again we could tell that because that had the lower number, so 4.5 is smaller, so that means it's more acidic. Okay. Alright, so why is rainwater naturally acidic? So it has to do with something that you have in air, is carbon dioxide. So the more CO2 we have in the atmosphere, you know, we already talked about climate change, but this can also, you know, it's such small concentration, we really don't get acid rain per se because of this, but it does result in acidic rainwater, and it's this reaction here where CO2 combines with water to give what's called carbonic acid. Okay, and so this carbonic acid, it's a weak acid, and so really this equation really should be this. Whoop, CO3. It should be that equilibrium, right? So you've got an H plus and an HCO3 minus. Okay, so this is bicarbonate, which you saw before. Okay, and that's your proton. Okay, so this is carbonic acid, and that is formed from CO2 reacting with water. So as rain is formed, rain droplets form in the air, CO2 dissolves in it, forms this, and then that gives you a pH around like 5, between 5 and 6. Okay. All right, so as I said, carbon dioxide concentrations is really not enough to cause, noticeable acid rain. Really, acid rain is produced from what we talked about in chapter 2. So it's the sulfur and nitrogen oxides. Okay, and so when you have, let's say, sulfur trioxide with water, that gives you sulfuric acid, which is a strong acid. And so you get, 2 protons in this case for every mole of H2SO4. And then let's say another one is nitrogen dioxide. And if you react that in water, you can get nitric acid. Okay, and that again is a strong acid. And so, this can wipe out forests, okay, or damage paint, on your, the clear coat finish on your automobiles, things like that. So these concentrations are really dangerous for acid rain. Okay. And so it's interesting that, rainwater is acidic, but ocean water is more basic. And so it turns out that you've got really 3 species that are responsible for maintaining pH in water, really waters, just not in ocean only, but in other lakes as well. And so it's carbonates, bicarbonates, and carbonic acid. Okay, so this gives rise to kind of acidity. And then if you have carbonate or bicarbonate, they will sequester protons. Okay, so if you have a proton plus this, it will bind to it. So it's actually removing protons from solution. And that makes it more basic. Okay, and so generally, if you have, I guess if I just go back here, so if you have a lot of like carbonates in solution, that will generally give rise to a more basic solution. Okay, so this is why, seawater has a fair amount of these carbonates, and that's why, for instance, mollusks and those, rely on carbonates to form their shells. Okay, so there's a fair concentration of this in seawater, and so that reacts with protons and it removes it from seawater, which gives it more of basicity. But the ocean pH is becoming more acidified as a consequence, again, of climate change. And so since we have more of this being formed, so more CO2 in the atmosphere that dissolves in seawater, your pH is going down and down, and so the carbonate ions are reacting with the protons, and so all of the carbonates that are in the shells of these sea creatures, they're now beginning to dissolve. So as the water becomes more acidic, now you've got a real problem that these carbonates that are in the shells are now being dissolved by all the added H pluses that we have in solution. And so you've got, again, it's kind of this equilibrium, right? So it's, you've got this plus protons goes with that, okay? And so if it's moving kind of in this direction, that's, it's good in that it's removing protons from solution, and then that way, the seawater is naturally basic, and it's kind of conducive to having carbonate that can form mollusk shells. But if you really put a lot more protons in seawater, now you're really forcing this equilibrium to really progress left to right. And so now you're really starting to remove a lot of carbonates that have formed in shells. And so it's a real problem with, sea creatures are now really dying because of this ocean water becoming more acidified. All right, so these are kind of the the equilibria that are all involved. And so we've got CO2 from, we'll just say smokestacks here, or cars. And so that reacts with water to give you carbonic acid, and then you've got protons. And so these protons then react with carbonate that, forms this bicarbonate. And so this is the coral that we have, okay, or, the mollusk shells, for instance, is another one. And so this is then being dissolved more because it's kind of forcing this in the left to right direction. As more carbonate is being dissolved by the protons, then more of this is dissolving. Okay, so this reaction is kind of forcing this to happen to a larger extent. All right, so as I mentioned, it's not just devoted to oceans, but also lakes and streams. And so here in the Midwest, we have a lot of limestone, and that's actually a good thing. So it actually neutralizes the acid, okay, and we call that acid neutralizing capacity. So in the Midwest, our lakes are generally not so acidic, but in New England states, for instance, or Maine in particular, they have large granite compositions, and so that's much less reactive, and so the lakes and streams are more sensitive. And so, it doesn't take that much, really. So normal aquatic life, if it's, maybe 7 to 8 in the pH scale, if you drop that down to like 6 or just below 6, that's enough to have many species of fish just disappearing. And by the time you get to a pH 4, where you kind of cut it in half, then your lake is dead. Aquatic life cannot live at all. And so that's a pretty dramatic shift. And something that, if you have granite-lined lakes, for instance, this can happen really fast. Whereas, here maybe in the Midwest, it will progress over slower time periods if things are not done to help the lake system. All right. I think that is where I will end then. We won't talk about water treatment. That gets into a whole nother topic. And so this is the cutoff for the final exam. We'll talk more on Wednesday about the final and any other questions you may have. But really, all the chapters, so chapters 1 through 5, all the way up to the end of pH, is the cutoff for the final. All right, so enjoy your evening, and I will see you all live, I guess online only, but live on Wednesday, where I'll take your questions. All right, take care.